Thank you for coming this morning. My name's Kevin Reinbold. I'm going to be the session chair for the 3DIC track today. My role within Siemens is I'm a technology manager supporting our advanced packaging and our 3DIC products. So the track we have lined up for you today, we have 2 sessions before lunch and then 3 sessions after lunch. Most of them are going to be focused on some of the challenges related to 3DIC. We got some interesting papers from folks from Microsoft, from Intel, Broadcom, chiplets, and also from Siemens. One of the themes you're going to see in all of those presentations is related to verification, some of the challenges related to that. I think as part of that, you're also going to see some of the scaling challenges that we're up against and some of the novel solutions that are being utilized today. As with the presenters are presenting, if you can, please hold your questions to the end. We are allowing time for a little bit of Q&A at the end of each session. So let's see what else. So if you have your cell phones, please silence those now. And with that, I'm going to introduce our first speaker. Our first speaker is Amit Kumar from Microsoft. Amit is a principal hardware engineer with the Microsoft's CAD team. He's responsible for the physical verification flows and methodologies around ESD, EMIR, as well as the 3DIC flows for their hardware products. He previously was part of the design enablement team at Global Foundries in Santa Clara. He's also worked as a technical manager for the worldwide EMIR and LVS teams. Amit has lived and worked in multiple countries, including the US, Germany, and India. Amit has managed project management, program execution experience. He's presented at a number of leading conferences and universities. He has a BE degree in computer science and engineering from the University of Rajasthan, postgrad diploma in VLS die design from CDAC in Pune, and an MS degree in microelectronics from Manipal University in Manipal, India. Amit is also a senior member of IEEE and IEEE Standards Association. He is a long-term volunteer at local food banks and community events. He likes to travel and learn about people and their cultures. So Amit's going to talk about advanced physical verification flows for 3DICs. Please welcome Amit up to the stage.
Thank you. Hey, good morning, everybody. So my name is Amit, and today we are talking about the 3DIC verification flows, and we will focus on verification, physical verification. So today we will briefly cover on the 3DIC. I know like most of you already are expert in 3DIC, but we will start with the basics, try to understand what is 3DIC, what are some of the challenges in the 3DIC. Then we will go in different analysis, including focus on mainly on the physical verification. We will also touch on the standards because this is the new thing. Everybody is talking about so many issues, industry in general trying to fix. So definitely we will talk about the standards and then go into the verification flow, starting with the bump and the PDN delivery, and then different type of checks we can do on the die, package, interposer level. And then we will look what XSI and Calibre 3D Stack offers to fix some of the physical verification challenges, and briefly touch on the shrinking, thermal expansion, and all those concepts, and then we will conclude with the summary. Okay. One slide only for Microsoft. So most of the people know that Xbox is the Microsoft only hardware. So that I think the first Xbox released in 2001 November timeframe. After that, we came along like long journey on the hardware, and that includes the third-party solutions and network adapter over the period. Last year in November, Microsoft announced their first AI accelerator and the CPU Cobalt. So those are our first product that we announced in 2023, last year, November timeframe. And from there, like our journey start and long way to go on the hardwares, right? Very basic, just try to understand what is 3DIC. And the picture shows little analogy, the Lego blocks. So till now, like most of the people, we start building like 2D in two-dimensional everything on the package. So in the 3D IC, basically we start building everything on top of each other. So there are different technologies out there from multiple foundries, OSAT. So in that, basically you stick all your component like simple ICs on top of each other on the side, and then you connect, right? So basically this technology allows the multiple stacking, vertical stacking. And depending on what type of technologies you are using, you can use hybrid bonding, TSV, you can flip those things and connect those things. This technology is widely used in mobile graphics and networking chips. So we will try to understand why these applications are basically we are using this, right? It enables, one of the main thing is it enables heterogeneous integration. We will try to understand in next slide. And recently we saw some papers or announcement that multiple companies are using these for the MEMS and photonics, where like in photonics, you are putting all your diode, transformers, everything on the silicon apart from the silicon device. So there are some announcements that people are using these for the photonics technologies also. So, okay, just try to understand why we need the 3D IC. So on the right-hand side, these are the 6 fundamental requirements that drives from 2D to 3D. So one is the cost, and all 6 are interrelated some way. So one is the cost. So cost means like as you are going to the lower node. So lower nodes are expensive. If you look at the blogs, 3 or 5 nanometer, one wafer cost like 5,000 K. So that is too much, like for the smaller or mid-sized companies to move into this space. So that is too much cost, right? To moving to the lower technology. That's why what we need to do, we need to divide our functionality into different parts. So that comes like modularization, where you can decide that, okay, which logic can be stay on the latest and greatest technology, which can be moved to the slightly older node. So that you can decide. Definitely yield is the major part. When you deal with the foundry, so foundry usually promise you that, okay, this will be our yield if you fabricate on our chip, our technology. So if you have a bigger side chip and there are defects on the wafer, then the yield will be less, right? So it results in the cost, higher cost. And then heterogeneous integration is basically you can divide your chip or the logic into different parts. Analog can still stay on the older technology. Digital can go on the latest technology. That's where like, okay, you can divide everything, you can put on everything on the one system. So that brings down the cost, right? So you don't have to build everything on the latest and greatest technology. It also provides the bandwidth, because in the 3D IC, basically your memories and everything are sitting exactly on the CPU, whatever you want to decide. So you can connect it vertically, so you don't have to access the memory sitting very far away, right? So that provides the bandwidth. And the reticle size is the last one, that as our chip size are growing, we are hitting the reticle size limit. So we have to break our logics into different things, different parts, right? Some of the challenges, so there are good things about 3D IC, but there are some challenges. So one of the main challenges is like the cost, overall system cost is high, and there are so many unknowns. So most of the companies start using these technologies, means 2.5D is since last 10 years, but all the latest and greatest technology, those are pretty new. So companies are still trying to optimize on the cost, but overall system cost is still too high. Their work needs to be done as industry. And then as we introduce new component like TSV, hybrid bonding, all those things that are like unknown territory, it provides additional complexity that we have to deal. Another major thing is the thermal, because now everything is sitting on top of each other, and when the chip is working, it generates power. There is no way to dissipate. So there are a lot of thermal effects we have to deal with. All the verifications needs to be done in that way. And then last and the most important is the standards. So in general industry, there is no standard at this point. There are few companies working on the standards there, but those are not fully functional yet. Another challenge is the flow. Basically, if you know the traditional IC, when you develop from RTL to GDS, you have to deal with only few things. But now you are dealing with the multiple flows together in the same timeline. So you have to work with the different teams, different engineers. You have to enable different flow that goes to enable whole system starting from die and different component. So that is also a big challenge on the 3D IC side. And then the data management. So data management, as we know that, okay, let's say our internal team is working on system design, so we have to generate the die level specs, all the component level spec on the system level. So those, then we, depending on if you are working with the foundry, OSAT, or mix of both, you have to take all the tech files, their collateral, use those into your environment so that, and then if you are using third-party IC or like some chiplet from the third party, so you have to integrate those. So you need all the bump location, everything, and definitely, so you can see that, okay, there are multiple things are involved here. So that adds the complexity, because to tape out, you have a certain timeline that you have to talk with the different team, move your data from one place to another so that they can do their analysis. It can't be happen in the sequential way. So now most of the things will go into the parallel. So there are a lot of challenges in that. So I will talk about little bit about the 3D blocks. So this is the one of the standard that TSMC introduced in 2022, and there are few versions available. So we'll talk about that, what it address. So at this point, like 3D blocks 1.0 and 3D blocks 2.0 is available, and there is a open source standards committee. Many EDA vendors and some other companies are working on that with TSMC. So when they introduced 1.0, their main focus was like, okay, because you think in that way that if you are building a system and at every step you need to perform some analysis, some verification. If you look at today, you try to use different EDA vendor, different tools. So bringing everything together, it's a nightmare, because even if you run one analysis in one tool with the same EDA vendor, and if you want to use different tool, you have to consider some like input and output migration. You have to change the file manually. And if that happens with the different vendor, then no way, like it will never work, right? So they understand, industry in general understand, TSMC understand. So that's why they put together, the main focus was 1.0 was when you move your data from one vendor to another vendor, one analysis to another analysis, everything should be aligned. So they try to address that. So they introduce a language, and they work with the EDA vendors to move in that direction. It supports all 3D IC structure, at least what TSMC offers at this point, and supported by, as I said, all the EDA vendors. In 2.0, they introduced this last year. So they took everything from 1.0 and they added few functionality, mainly all the pre-analysis, because once you build a system, that will be too late, right? And then if you are moving your bump and everything at that point, so it will be too late. So they allow some prototyping and design reuse concept, and allowing that you can do most of the analysis at very early stage, right? And they introduce multiple flow, abstraction level. If you don't have anything, you can run a black box flow at initially. Then once you have left def, you can run on that. If you have a final GDS, you can run on the final GDS all the analysis. So that's how it works. There is a open source standard, 3dblocks.org, means people can download the specs and everything for both from that location. Okay. So this slide shows that we did some experiment, try to use 3D blocks in our environment. So as the concept of the 3D blocks, and this standard is like you can use the data from one vendor to another and port it for different applications. So we use from third-party EDA vendors, we use the 3D blocks file generated from that tool, and we try to use into XSI. And basically, simple example, we can able to import, change some property based on our need, and then we are able to run the full flow. But just try to understand how 3D blocks work. So this is not a one file, right? So this is a bunch of file. They call 3DBX file. So that file basically define overall your system. Means if you have, for example, if you have multiple 4 die SoC tops, you have HBM memories and interposer, everything, right? So you need to create 3DBX file for each component, right? And one top level file that is 3DBX. I recently learned that they are also introducing 3DBF file for the feasibility studies. But looking at this, right? So you create one 3DBB file for each component where you define all the important component, like from where the left, def, GDS, that particular component bump map file. So they have a specific requirement for bump map also. Once you define that, then you, in the 3DBX file, that is the top level file, basically you combine everything, you include all the 3DBB file, and then you make a system there, you define which component connect to which component in what region. So that once you define that, so most of the things are like tool will automatically take it and use it for your analysis. Previously, we used to do all the setting, all the GDS, left def, everything by hand. So that is like good first step. I consider 3D blocks. That's helping, right? And then once you run in the design in the 3D stack, you can result all the view and debug accordingly. Like those are familiar with the Calibre, right? So it's the same Calibre interface. So now let's go a little bit about the verification. On the physical verification side, mainly everybody knows that we are focused on DRC, ESD, connectivity, and all those things, right? And the tool basically supports almost everything on those points, right? So I will not go into detail, but this is just for understanding. One of the important thing is ESD, because currently we are doing all the ESD till the die level, SoC level, right? But as you know that, okay, some of the connections might be going from one die to another, some powers, ground, they are going directly to the package and those things. So we have to account for the ESD. So in ESD, mainly we do like point-to-point and current density checks. And at this point, this whole flow is little bit immature. So we are doing at die level, and then individual path we are trying to do, but there are work needs to be done on this ESD front, right? But this is also we can consider into the 3D IC verification. Let me start on the flow basically. So typically what we do is like when we try to build everything, we start with the bumps, and sometimes we get bumps from the foundry, sometimes we create our own bumps. So we create a bump library, basically different configuration with the prop pads and everything. And then using those bumps from the bump library, we do a SoC planning, okay, what bumps will go where, right? And then once we freeze on the location, we give this to the interposer, different team and different format. And then they will do the interposer planning and everything, right? And the package, all the bump alignment, because end of the day, bump should align to SoC, package, and from down, like C4 bumps also needs to be aligned, right? The second analysis, what we do is we create a stack. We take from few layers from the die, and most of the layers from the interposer go all the way to the package. We define all the resistivity and everything for each intermediate layer, and then we run the extraction and the simulation on that. So what that gives is that gives a heat map that tells that, okay, if all our bumps, if some bumps are connected to supply and VDD, VSS and different, so if the current will flow where those are very close to each other, where areas are little hotter, right? So that gives that analysis, and based on that, we just move our bumps here and there just to do that analysis, make sure that everything will be all right, there will be no hot spot later, right? And that's how we fix those things. On physical verification, I divide this into multiple segments. So basically, everybody knows the SOC level, you do whatever the physical verification checks you got from the foundry. That includes the DRC, LVS, ERC, antenna, you name it, like there is a big list of it, right? So at the SOC level, you try to make everything clean. And then if your connections are going from one die to die, so usually you take a CDM-based ESD checks and some of the DRC placement checks that you run. On interposer side, depending on if you are using a foundry OSAT, they provide their own foundry decks. So that might include the DRC, LVS. So you want to make sure that interposer itself is clean. And then once each the component is clean, at the system level, on the physical verification, you all care about if everything is properly connected, aligned, right? So all the aligned and the connectivity is there. So on the verification, basically, what our best practice is we start early, and even some of the components, when those are not ready or work is going on, we try to start that flow that time. And in our flow, we try to use GDS, OSS, ODBB++ coming from different tools, so we can use everything, right? And we can run this flow at multiple level. Let's say if you have only the SOC available and the interposer package is available, you can at least run the alignment check. Once you have fully routed interposer, you can run all the connectivity and everything. So in your analysis, basically, you can start with one component, add second, then third. You can, depending on when you are getting the data, you can enable those flow, right? So that's why, like, before combining everything together and debugging, so we try to make sure that at least individual components is clean first, and then we hook up both together, and then if both are clean, then we hook up third one. And as the data comes, we try to replace everything. So that is like a streamlined flow we try to work, right? On XSI, so we are using XSI, Siemens XSI and 3D Stack for physical verification. And this gives a good feature to us, like it understands all the format, input format. You can generate all your system level local netlist into this, and you can run the caliber, you can debug some of all the connections and everything, all the debugging you can do in XSI. It also supports the scaling and everything, right? So that's why we are using at this point. Little bit, let's understand what the 3D stack checks usually do, right? So the good thing is, like, in this flow, you don't have to wait for foundry DAC. So the tool basically checks most of the fundamental checks itself. It creates on the fly run set for you. So one of the thing is like text and port text. Like if you see that, it also check if some bump has a multiple text sitting there, so it will give a violation. If some bump doesn't have text, it will take that. So all sort of these things the tool will report, right? User has flexibility. If, let's say, if they are very early, they don't have routing for interposer and the top, they only care about the alignment check. So they can enable and disable these kind of check based on at what stage they are, right? So a lot of flexibility there. So this is like a little introduction how 3D Stack and XSI works. So basically, 3D Stack is a cockpit that you can enable from the XSI. So XSI tools offer multiple feature. Usually we use, like when we have all the data, even the incomplete or the complete, we try to use XSI and enable everything into the XSI. You can define your system, whole system into XSI, and then you can translate that to the 3D Stack cockpit. The 3D Stack cockpit, what enables you is like you can, once you define everything into XSI, you can add individual component level properties. If you know that, okay, if I have a SOC, what is the bump layer I'm using? So you can define all the fine details in the property manager. Even you can, if you have a connectivity for the interposer, what RDL layers connect with which layer, right? So with the passivation layers and all those things, so you can define all your using all the connected statement into this. And then once you translate everything into the 3D Stack, there basically on the system, you can control what analysis you want to run. If you want to exclude, let's say you have a multiple discrete component on the package that you don't want to include for this analysis, you can exclude those. In, you see the bottom, there's a red exclude. You can, there are buttons that you can simply move up and down, left and right. So very easy to use tool. You can move things around, and once you know what you want to run, even before hitting the run, you can generate the files for different analysis and see that whatever you are trying to do, if that is there or not, right? And then once you are sure that, okay, this is what you want to run, what you can do in the tool, there is a bottom, there is a one-click generate. So you can hit that, it will generate all the tech files and the files run set for you. You definitely don't need any Foundry tech file or the run set file for this. You can hit that, and then it will run the actual 3D stack, the tool Calibre 3D stack, and you can view your results in the RV, same whatever you are doing in the Calibre. XSI provides so many utilities we are using day-to-day basis. Like depending on what you want, you can use different utilities either provided in XSI. You can write your own skill or own scripts. We are using combination of both. I mean, some example is like if you want to split your bump map, top side, bottom side, combine, you can do that. You can, if you have a GDS only, you can port to the map file, CSV file. So there are a lot of functionality available in the tool. You can do this thing. And even you can write your custom scripts that you want to run. One slide on the optical syncing. So basically, you know, like nowadays, if you look at any Foundry, typically they offer, for each node, they offer multiple technology, and performance-wise, little bit different. Sometimes they offer a technology that is simply an optical sync, means that you don't have to redesign your thing into that particular technology. You can stay on the main node, and Foundry will take your GDS and they will apply a global sync on that, and they will sync everything, right? Historically, we have see like only the device level syncing, where you can design your thing, chip, and if you want to size only a device, you can put a marker, and depending on the marker, Foundry will apply the syncing. So, but these technologies are like, they will sync everything, right? So you don't have to port your design from one node to like a subsequent advanced node, right? So the problem with this is like, let's say your packaging team, if you are using third party or OSAT or different Foundry, and if they are not using sync technology, only your Foundry is providing a sync technology, then end of the day, when you try to match all the micro bumps on top of each other, it will not match, right? For your analysis, you need that flexibility into the tool. So tool provides that you can apply the shrinking on whatever level, and then you can enable, so it will automatically generates you the shrink view that, and then if you run your analysis on that, so most of the time perfectly it will match, right? Another feature is on the package expansion. So the thermal package expansion coefficient is basically the package is different material, and depending on the temperature, it sometimes expand, right? And the same analogy, like if let's say you put your analysis and if your package expand, then it will not completely overlap, right? So those kind of coefficient also you can apply into the tool, and you can do all the analysis accordingly, right? So that all the features are there into the tool. Some of the future enhancement, basically what we are working with our partners. So definitely 3D blocks standard is one that we are looking forward, and new, sometime like on the paper there are advanced thing, but EDA vendors are just catching up. So not everything is ready. So we are working with that. Definitely, we only covered about the physical verification. There are a lot of verification, and if you look today industry, and if you are trying to do from starting to end, including the thermal and all those things, you have to use almost all the tools available for that particular EDA vendor, different tool. It's a big no-no, right? And then once you do that, you have to port your data from one format to another, lot of time consuming thing. So definitely we need a unified solution where you can pick the tools from different vendors, you can pick the analysis from different and run those things. So these are some of the enhancement we are working, and also enabling some of the other analysis in our tool, right? And definitely, as I mentioned, standard is one. So that will give like, okay, we can mix and match all the tool and analysis in the faster way. In summary, so everybody knows that, okay, at some of the advantage of 3D IC is like, okay, this is enabling us for generating a low power, high performance, high bandwidth chips into a 3D manner, vertically stacking. There are a lot of challenges. Industry just, I think, started. So many people start working on this. There are work needs to be done on this. We are working with the foundry and EDA vendors to develop some of the solutions, at least for us, or like a broader ecosystem, right? And definitely industry needs a standardization on not only from the TSMC. I personally think it should go beyond any foundry. It should be for the general ecosystem. So that's all I have.
Thank you for watching. To learn more about this topic, check out the links in the description. And if you enjoyed what you saw, like the video and subscribe to the channel.